We've shown that matrices can be used to represent symmetry operations, and what I'd like to do in this video is make a case for using these matrices actually as a way of representing the entire point group. Now, I've written up here, this is strictly for the point group C2V. I want to use that as an example. And I've written up here the matrix representations for each of the 4 symmetry operations that are present in the group. So we've got the identity operator, we've got the C2 rotation operator, we've got sigma V reflection operator, and the sigma V prime reflection operator. And so we're going to essentially designate the C2 axis as the Z axis. We'll designate the sigma V operation as the XZ plane and the sigma V prime as the YZ plane, just so that we can draw pictures of this eventually. I've also reproduced the group multiplication table for C2V, and that's shown over here in the upper right. So what I'd like to do is simply demonstrate that using these to represent these operators will in effect reproduce this group multiplication table. And I'm not going to do it for the entire table, but if we were to, for example, look at the successive operation of the C2 symmetry operation and the sigma V symmetry operation, the table would tell us to come over here and to look at this element. So that would be sigma V prime. So is that what we get when we use these matrices? Well, what I'll have is C2 matrix with the sigma V matrix would simply be -1, 0, 0, 0, -1, 0, 0, 0, 1 for C2, and for sigma V it'll be 1, 0, 0, 0, -1, 0, 0, 0, 1. And since these are both diagonal, it turns out I can do something actually easier than just normal matrix multiplication. Basically, since they're both diagonal, the only elements that will survive are this times this, to give me the upper left element, which is -1, this times this, which will give me the middle element, which is 1, and this times this, which gives me the lower element, which is 1. And the rest will all be zeros. All right, well indeed, when we look at this, it is equal to the sigma V prime. So in essence, we can show using these matrices that the matrices themselves obey this group multiplication table, and so they are a good representation of the overall point group. Now, you might ask, is this the only matrix representation that would work? Well, in fact, it's not. And in fact, it's also not the most useful one or the most efficient one that we could possibly devise. In fact, there are an unlimited number of matrix representations that could represent this particular point group. And one of the things I want to do to persuade you of this, there are more mathematical ways to show this, but I think rather than getting heavy into the math, let's use a more simple example. Is I want to draw our coordinate system for this particular point group. So here's our z-axis, and it represents C2. So this is the z-axis, this is our y-axis, and this is our x-axis. So we have one plane, which is the yz plane, and this is sigma V prime. The C2 axis is the z-axis, and the xz plane this one is the sigma V plane. So it is the one that would be a reflection about the xz plane. All right, so now what I want to do instead is imagine that I have a vector that's simply along the x-axis. So I'll call this vector u sub x, and I'll put a little arrow over it to indicate it is a vector. So our vector is down here, ux up here. And what I want to do is look at what each of these 4 operations in the C2V point group does to u of x. Well, the first one is pretty easy because the identity operator doesn't do anything, it leaves it as u of x. What about the C2 operation on u of x? Well, C2 is a rotation about the z-axis, so it will rotate u of x back in this direction, which means in effect what I've done is I've got negative ux. All right, when I look at the sigma v operation on u of x, Okay, sigma v is the plane that u of x lies in, so it does not change u of x either. But sigma v prime is this yz plane, it's this plane over here, and so it again will reflect u of x back into this vector, so I'll get negative u of x. All right, so in effect what I've done using this simple one-dimensional vector is I have taken these four operations and I could write them as follows. The effect of operating the identity operator is to multiply by 1. The effect of rotating is to multiply by negative 1. The effect of reflecting here is to multiply by 1. And the effect of reflecting here is to multiply by negative 1. So in other words, I have these as my new representation of this particular symmetry group. Now this may seem particularly simple-minded, but in fact this is a perfectly good representation, and you could show that these four numbers together correlated with these four symmetry operations will also obey this group multiplication table. It's also true that each of these has an inverse, and each of them is its own inverse. All right, so it obeys the properties of a group. Associative property should be obeyed by these simple numbers. So in effect, what we've done is we have created a representation of the group using one-by-one matrices, if you want to think of these as a one-by-one matrix. All right, and one can do this for a variety of different types of operators. One that in particular I'd like to point out is the C3V, which would be the point group for something like ammonia. And one of the things that C3V includes is, well, it's got a C3 axis, and that C3 axis has as its symmetry operations both C3 operated once and C3 operated twice. But these two operations are related. They use the same rotation axis, and as we've already noted in an earlier video, this one is effectively equal to C3 operating in the reverse direction. So in some sense this is the inverse of this one. But the whole point is that because they are related to one another and they involve the same set of transformations, that is rotation about that axis, we say that they are in the same class. So this is a class that has a dimensionality of 2. All right, and because this is a rotation about 2 pi over 3, that's what in effect what the the C3 rotation means. It means that every time I rotate, I'm not rotating by pi or by pi over 2, or by pi or 2 pi. I will be mixing x and y together, much as we did in that video showing how matrices could be used to represent symmetry operations. If I'm mixing these together and there's no way I can prevent doing that, then I am inextricably limited to a two-dimensional representation for this particular symmetry element and these particular symmetry operations. All right, so that makes things a little bit more complicated than they are in this case, where everything can be one-dimensional as I've drawn it here. We'll see how these things work when we get to the point of taking these representations, like the original representation that I have up here, which is a reducible representation. And we can take this, and there are systematic mathematical ways, we won't worry about that, but there are systematic ways to take this and from it deduce irreducible representations. And it's the irreducible representations that we'll care more about in the long term. In effect, this is a reducible representation. This is an irreducible representation, these one-dimensional ones. So we'll see what that looks like in the coming lessons, but it's what will make group theory actually a very accessible, hopefully, enterprise for all of you to work on.